Hello everyone, I'm Aryaman and I will be presenting our progress on the research topic Design and Fabrication of SMA-based 4D printed actuator for FWMAV. We are a group of 5 working on it. My friend Siddharth and I are third year BTech students while Mr. Rakshith and Mr. Saiyadali are PhD students. The project is under the primary guidance of Professor Somashekara, whose research interests primarily lie in 3D 4D printing and additive manufacturing. I'd like to thank our professor for giving me this opportunity to be a speaker at the conference of 4DMDA. Before I begin, I would like to mention the journey of my institute, IIT Dharwad. It has come a long way from 2016, when classes were taken by IIT Bombay faculty, to 2022, when we have rupees 10 crore funded research projects. The permanent campus construction is in full swing and R&D labs have been set up. These are the contents which I will brief through in the next couple of minutes. To start, a brief introduction on the topic before diving into the technical details. Flapping wing microaerial vehicles, abbreviated as FWMAVs, are made to mimic the flight of a bird that flies by flapping its wings. The traditional FWMAVs are powered by DC motors coupled with gear mechanisms, which increases the entire structure's weight. We intend to reduce the bulky mechanical mechanisms and motor to a simple SMA actuator. SMAs offer great potential based on the inherently high work density, which is roughly 25 times greater than the work densities of standard electrical motors, which makes them a suitable replacement. They mimic natural birds, so they pose an excellent resource for aerial reconnaissance, wildlife survey, and navigation through humanly inaccessible regions. Moving on, some of the literature which has proved helpful in our research is mentioned here. In this paper, the authors utilized the natural frequency of the actuator to attain maximum stroke angle out of it. They also attained up to 35 Hz of flapping frequency with SMA wires of 38 micron diameter. They used two sets of wires for two-way actuation to produce the flapping motion. They used a PDMS matrix, which is a soft and flexible material, to keep the wires in place and prevent environmental damage. Another paper shown here which has worked on a similar concept. Their actuator is designed such that the actuator also twists slightly during the upstroke to produce greater net lift force for the wing attached to it and reduce its drag. Now moving on to the objectives. The first objective is to design a 4D printed SMA actuator that performs the flapping motion. Then evaluate the performance of the actuator using parameters such as the stroke angle and the time response. Nitinol is a non-linear material which is comparatively more complex to model than a linear one. However, we have used the Euler-Bernoulli model applicable for linear materials only and compared it with a simulation resulting in the elastic range. By applying boundary conditions of zero displacement and zero bending on the fixed end, we have used the Euler-Bernoulli equation to model the 75 mm long and 1 mm thick SMA wire, similar to cantilever beam. As you can see here, after obtaining the relationship between the deflection of the free end with the load applied to it, we have compared its plot with the one we obtained using ANSYS simulation of the same. One of the critical factors we face with shape memory materials is their heating and cooling rates, as heat is the chosen stimulus. The heat is caused due to Joule heating, which is caused by current passing through a resistor. As we observe, there is a loss of heat due to the convection taking place. Taking all of these into account, the heat transfer equation for the wire is derived from the first law of thermodynamics as follows. On the left hand side, the MCP delta T term is the net heat energy stored in the wire. The ML term is the heat energy lost due to latent heat of transformation of the shape memory material from martensite to austenite. On the right hand side, you can see the heat loss due to convection and heat generated due to Joule heating. These are the parameter values we used to calculate the total time required to heat the SMA wire from ambient temperature to its austenitic finish temperature at 80 degrees Celsius. It is obtained as 3.53 seconds. This is the schematic of the pathway to achieve our main objectives by identifying the relevant variables, requirements, and constraints. As we can see here, the objective is to achieve high stroke angle, high payload, and high actuation speed, for which we have multiple dependent variables at play, such as high net force and high rates of heating and cooling. For higher net force, the matrix should be soft and flexible so that it doesn't resist the recovery force, and high quantity of shape memory material will result in high recovery force. So, higher the amount of SMA wires, the more will be the force produced. For high rates of heating and cooling, we propose to use thin SMA wires, and using high electrical power will also increase the joule heating rate. As discussed in the previous slide, the matrix should be soft and flexible, for which the proposed materials were 3D printed elastic 50A UV resin, TPE, which is thermoplastic elastomer, and siloxane elastomers such as PTMS. The final materials used was thermoplastic elastomer because of its ease of 3D printability. Our aim here was to use 4D printing to develop the actuator instead of creating a mold of siloxane elastomer as a matrix, which was the case in the published literature. The final design of the actuator is shown here with equally spaced SMA wires inserted into the TPE matrix. We simulated the load versus tip deflection relationship of the actuator prototype in ANSYS and plotted the results as visible. To prepare the actuator, we first created the fixture to train the SMA wires. 4 such wires of 75 mm length were placed in the fixture as shown, with a bending angle of 70 degrees. Then the fixture was heated up to 540 degrees Celsius in a furnace and immediately quenched afterwards. As the wires trained, they were finally inserted into the TPE matrix. This was our experimental setup. We conducted experiments to measure stroke angle and the time response of the actuator. The equipment used can be seen in the figure. The DSLR camera was used to click pictures and record the actuator in action. Clamps were used in the experimental setup to fix the actuator at one end while keeping the other end free to bend. Thermocouple was used to keep track of the temperature of the SMA wire, and finally DC power supply was used for joule heating. For stroke angle and time response, we use the Image software to measure the bending angle and a video player software to analyze the recorded videos to measure the time response. Here you can see the image of the actuator before actuation and bending due to joule heating afterwards. This is a real-time video of actuation of the TPE matrix with 2 equally spaced SMA wires inserted into it. The total current provided was 6.4 amps. Moving on to the results, it was observed for a similar actuator of different dimensions with 2 wires inserted into TPE structure that the matrix reduced the bending angle of bare SMA wires by 26.37 degrees. Tabular data on this is shown. This is the data on stroke angle and time response that we measured using the previously shown experimental setup. At first, the current was varied while voltage was kept constant at 32 volts in the voltage power supply unit. Secondly, we varied the voltage while keeping the current constant at 6.4 ampere. These are the graphs for stroke angle and time response obtained plotted against the total electrical power. To conclude, thermoplastic elastomer material used has proven to be a viable matrix due to its high flexibility and good 3D printing capability. Actuation speed obtained for 1 mm diameter SMA wire is not optimum for high-speed flapping applications. Hence, thinner SMA wires should be used for higher rates of heating and cooling and thus higher speed of actuation. This is due to higher rates of convection. Electrical power usage should be minimized so that the powering and FWMAV is possible using small and light battery units. Our future work will consist of doing more experimental work on the current model, building a two-way actuator and evaluating its performance so that the flapping motion can be achieved, attaching a wing to the actuator model and measuring various aerodynamic variables such as thrust, drag and lift. Here is a conceptual CAD design for FWMAV that we have proposed for the upstroke, for the downstroke, and an isometric view. This research work is supported by the Science and Engineering Research Board, Department of Science and Technology, Government of India, under Startup Research Grant Scheme and Technology Translation Award TETRA. The authors acknowledge the support of sophisticated central instrumentation facility in IIT Dharwad for carrying out all the mechanical and material characterization. These are the references of the major literature which we used in this presentation.